All right, it should be recording. All right, you don't have to turn on your cameras, but if you do, just know that you're gonna be recorded. It's gonna be posted on. It's probably gonna be posted on YouTube, just for future reference. So just keep that in mind. All right, psychrometrics. So at first, I'm just gonna share something funny. I thought it was actually called psychometrics at first, but it's actually called psychrometrics. Has an extra R in there. If you have psychometrics, it's like it's a different thing. So anyway, all right. So first off, we're gonna start off by just reviewing how the psychrometric chart works. So we're just gonna go over the different components down here. Right at the bottom, we have the dry bulb, or I think, yeah, the dry bulb temperature. So this is what you would just read normally on a regular temperature. And then up here across this exponential line, you would have what you would call the wet bulb. Wet bulb temperature. So just to put it simply, if you have a thermometer, you fully saturate it with water and you let all the water evaporate into the air, you get the wet bulb temperature. Up here you have enthalpy, which is measured in BTUs per pound of dry air. And that's also across this axis of wet bulb. You can see the wet bulb temperatures, you can see the enthalpy sort of lines right there. And you also have humidity, relative humidity. You have absolute humidity over here. You see the humidity ratio, pounds of moisture per pound of dry air. So that's just relative humidity right there. Then you also have the enthalpy measurements, BTUs per pound of dry air over here. So you have these straight lines. And then you have humidity right here. All right, so just a simple way to think about this is x-axis, temperature, y-axis, humidity. That's like the most simplest way to think about it. So let's just take an example. Let's say you have 90 degrees. You have 90 degrees dry bulb temperature. It's the measuring you get on your thermometer. And let's say you just have 40% relative humidity. 90, 40. Right about there. So you can see the 90, I just went straight up. And then the 40%, I just went across this exponential curve. Now we want to find wet bulb temperature. So what is wet bulb? So you can think of sort of like you're taking the current temperature and you're fully saturating it with water. You're bringing the humidity up to 100%. And to get there, you would have to, I forget. Shoot. Sorry, I was not prepared for this. I should have done more preparing.
Isn't it like put a sock over the bulb?
Yeah. So you put a sock over the bulb. So the sock's completely drenched with water, and then you swing around to add a little bit of energy to it to evaporate it. And then you would you get the wet bulb temperature. I don't remember if it's okay. All right. I got it. So in order to get the wet,
my slice.
Huh?
Ali, where's my slice?
All right, I feel much better about this. Wet bulb temperature. So in order to get the wet bulb temperature, you would need to just go along this wet bulb axis right here. So you see these darkened lines right here? That's actually enthalpy because these line up with the measurements off to the right over here. The wet bulb slope lines are slightly different. They're sort of more steep almost. So you can kind of see that right here. You have the enthalpy right here. I'm just gonna do the wet bulb in blue. Okay, so I'm gonna draw the enthalpy in red right here. So you can see the enthalpy line right there, right? And here is the wet bulb temperature line. You see how the blue is slightly lower than the red over here, and the blue is slightly above the red over here. So there's a bit of a difference, but like if you're just like doing some general calculations, you don't really need to worry about it. But if you're doing like real engineering things, you probably have to worry about it. All right. So so we're just gonna go straight northwest. Oh God, that's not a line. Go straight northwest from this point. Remember, this is the 90 degrees and the 40% relative humidity. Just go straight up, somewhere around there, and you would go straight down from there. Remember, the x-axis is the temperature, so you go straight down. You get a reading of 70 degrees. 70 degrees. Let's go down that axis point. So 71 degrees. That's your wet bulb temperature. Right. So you're adding as much moisture as you can to the dry bulb temperature to reach the wet bulb temperature. And you reach this 100% saturation line right there. Any questions? Cool. So now there's also dew point. Now what's dew point? It's essentially, all right, you're given this climate. You have this climate. At what point will this climate, at what temperature in this climate will water start to condense? So if you think about it, you're not changing the humidity. So you wouldn't worry about going up and down the y-axis, right? Because remember, y-axis is humidity. You won't worry about going up and down the y-axis. You would just be lowering the temperature down. And if you think about it, when you lower the temperature and it reaches this 100% saturation point, water will start to condense. That's your dew point. So you just go straight west and then go straight down to around 62.5 degrees Fahrenheit. And that would be your dew point. So review, you get the dry bulb, get the relative humidity. You go northwest for the wet bulb. Make sure you go straight down to get the temperature reading. And for dew point, you're going straight west and going straight down to get your dew point reading. I'm just going to draw in the dry bulb temperature right there. So we have a bunch of different ways to talk about temperature, all different ways of thinking about humidity and temperature. Now, enthalpy, it's just, I'm not really sure how to explain it. Enthalpy is sort of like the energy inside your climate. So if you think about it, you add more temperature, you get more energy. So you go add more temperature, you see how the energy goes from 35 to 40. If you add more water, it'll get more energy. So you go higher, you go from 35 to 55. But what if you add more energy and take away some water? Well, it'd stay about the same. It's around the same slope. So enthalpy is sort of like the energy that's inside the air / climate. Does that make sense for everyone?
You kind of cut off a little bit earlier, so I didn't really hear what you said earlier.
Okay, might be the mic. But does anyone have any questions? Cool. All right, so basic stuff. Let's just do another practice example, I guess. So someone shout a dry bulb temperature.
76.
76 degrees Fahrenheit.
31.
And then 31
Seems
relative
fitting.
humidity. It would be 31%. Beautiful. All right, so now we're going to find Enthalpy, I'm going to find wet. Okay, first we're going to find wet bulb. Going to find dew point. I can't type. Then we're going to find enthalpy. And I think that's, oh yeah, also we can also find absolute humidity. Absolute humidity. All right, so beautiful. So first we're going to plot these 2 points onto our graph. So you always need 2 points to plot. It doesn't matter if it's dry bulb or relative humidity or wet bulb and dry bulb. You can figure it out. But first, let's find like a good standard with relative humidity and dry bulb. So dry bulb 76 degrees Fahrenheit. That's gonna be right there. And then 36. Yeah, right around there. So
Wait,
we're
where'd
gonna
you get
have
36 from?
oh frick, 31. I'm
Ooh,
tired.
Slipping up today, Buster.
Oh no, I'm so sorry. 31 degrees. All right, 76, 31. What blamio? Everyone on board with that? That is our 76 degrees, right? Yeah. And that's our 31 degrees. See, there's or 31%. So there's our 30. Let's just go a tenth above and bam. So that is our current climate. Cool. So let's find the wet bulb. So what we're gonna do is we're just gonna take this slopey line right up here. We're gonna reach the maximum saturation point because once air is fully saturated, you can't add any more water to it, right? So you think of it as a cylinder. You can keep adding more water, but eventually it's gonna spill over. Now, if you increase the size of the cup, well, that would just be increasing the temperature. So you can add more water. That's why this exponentially grows. The bigger the cup gets, the more water you can add. So like when temperature becomes higher, it becomes more active. It expands, meaning it can hold more water. That's why it goes up. And that's why relative humidity is different from absolute humidity, because it depends on the temperature of the air. Probably depends on atmosphere too, but I don't think it's like it's on here.
That's actually a perfect example right there.
Yes. All right. So wet bulb, you just add as much water as you can while also decreasing the temperature, and bam, you reach there. Go straight down on that axis, and you get 56, 57, 58 degrees Fahrenheit. Text. 58 degrees Fahrenheit for our wet bulb. Dew point. So you're not adding water anymore. You're only lowering the temperature. Think of like your lawn outside. You know how it gets like super cold in the morning, and then when you wake up, you see dew on like leaves or something? That's sort of like what we're doing here. We're just lowering the temperature. We're not adding any humidity of our own. We're just seeing what temperature does our current humidity need in order to fully condense.
Oh, so you just run it all the way to the left, and then you go straight down to find your temperature?
All the way to the left. So remember, we're only lowering the temperature to reach 100% saturation. We're not changing this absolute humidity at all. Speaking of absolute humidity, we can just go over. You can see 0.006 pounds of moisture per pound of dry air. I'm just going to put 0.006. 0.006 pounds. So we stay at that absolute humidity. And you're going to notice the relative humidity changes because it's getting colder, the container's getting smaller, so it can hold less water. And once it reaches its capacity, the saturation point, it condenses. Go straight down, and you see, wow, our freaking thing is like 9 degrees Fahrenheit. Wait, no, that's, no, stop. Okay, 43 degrees Fahrenheit, geez. 40 degrees Fahrenheit. See, I thought this was our measurement, the BTUs. Don't make that mistake. Oh, geez. We sort of had a long day in our class. Anyway, not making any excuses. So let's just take our enthalpy, bam, bam. You can line up the lines with these sort of tick marks that you find on the edges. So you see there's like a bunch of these tick marks, and then there's these tick marks too. So you just line those up to line it up with the enthalpy readings. So now you have something 20, 1, 2, 3, 4 point, 24.8. Bam, bam, 24.8 BTU per lb pound. Everyone follow along? Everyone understand? Everyone who doesn't understand?
So how'd you get the 0.8? Cause I saw you count in the bottom, because I know right here this area is like 24.
Oh,
and
down here?
Yeah.
Okay, so 20. So you have 20 and then 25. So you have 1, 2, 3,
Oh, okay.
4
Yeah, I
tick
didn't
marks.
see that.
It's kind of hard to see maybe on the streaming, but yeah, 20, 21, 22, 23, 24, and then there's 4 more ticks right there. So it's divided into fifths, 0.2, 24.2, 24.4, 24.6, 24.8.
Yeah. Okay. Yeah, I just didn't see that point, the little small things on the bottom. That's why I was just like, wait a minute.
So yeah, if you're like ever confused, you can like use the major and minor tick marks to help you count. All right, cool. We're just gonna do another one, just really quickly, just as a quick fire round. All right, we're just gonna go here. We're gonna choose a random point here, and we're gonna determine everything from this point. All right.
قدام الشاب.
So we have our dry bulb. Just go directly straight down. This is your current climate. You don't have to change anything. Just go straight down to find the temperature. 93 degrees. 93 degrees Fahrenheit. Bam, that's our wet bulb. I mean dry bulb. That's our dry bulb. 93 degrees Fahrenheit is our dry bulb. Bam, relative humidity. You just read these relative humidity lines, 40, 50, somewhere between 40 and 50. It's like 43. Relative humidity is around 43%. Wet bulb, we're adding water and it's lowering the temperature as well. So we go diagonally, bam, up to there. Saturation line, it can't hold any more water. Go straight down, and that's 74 degrees. Your wet bulb is 74 degrees Fahrenheit. Let's look for our dew point. We're just lowering the temperature until humidity reaches 100%. Bam, we're not changing the humidity we're not changing the absolute, we're just changing it until it reaches 100% relative humidity. Go straight down, make sure you follow the axis, and 66.5, sure. Dew point, 66.5 Fahrenheit.
Wait, are we allowed to use 0.5?
67 degrees Fahrenheit.
Okay, because the other one they said for us just to round it up from the 0.5.
Yeah, that's true. All right, so now let's just do the thing, enthalpy. So I'm just gonna line up on the major axis first to make my life easier. I can tell. Yeah, that's close enough. Enthalpy, bam. Oh wow, this is like, no wait, that's not. 35, 36, 37, 37.4 or 6, 37.5. To just do that just by reading the tick marks, enthalpy is 37.5 BTU per lub pound. And then one more, it's absolute humidity. You just go straight east, 0.014 pounds. So absolute humidity, 0.014 lubs. All right, cool. I think that's all you need to know.
Hey man, this second problem right here, perfect. Honestly, absolutely perfect.
All right, beautiful. Does anyone have any questions? Does everyone understand?
I actually understand this now.
Does everyone understand?
Yes.
Better than
Oh,
I did in
Emron's here.
class.
Emron, my guy, what are you doing here?
What's up? I was totally not napping after class and joined late. Totally not.
This dude.
We had to watch a movie after class for our studio. Oh boy.
You had to watch a movie? Oh no.
Yeah. All right.
So sad.
Hang on, quick question, off topic. How do you get your kitten to stop biting you?
don't?
Adoption. Put up for adoption.
It keeps
All right.
biting my hands and feet.
You give it love and affection. That's what you do.
I do give him love and affection. He bites me in return.
Yo, so
You just want
Edison,
more.
did you just come up with these problems? Or this
Yeah,
is-
it's just random numbers. I don't
We
have
just
anything
random
written down.
rouletted.
No, yeah. Because Van Lanningham never posted the homework. He played us all.
Yeah. Actually, do you want to do a problem where I like don't give you just the dry bulb and relative humidity?
I mean, yeah, I don't know what kind of
Right,
problem
yeah.
give us, right?
All right,
Yeah.
cool. All right, so all right, so I'm just gonna. So we have 6, I think, measurements we can get. Dry bulb, relative humidity. Okay, I'm just gonna go dry bulb, wet bulb, dew point. Now we have relative humidity, absolute humidity, and enthalpy. So I'm just going to do is I'm going to go to random.org.
Nah, close your eyes and then move your mouse in like a circle thing and place it down.
No. So we're trying to get measurements. We're not trying to get. We're trying to get measurements. We're not trying to get like a point on the graph.
Oh, okay.
All right. So move number 6. All right. Random.org gave me 6. So we're going to get an enthalpy measurement and another one 5. Absolute humidity. Yeah, that'll work. All right, cool. So, absolute humidity. Give me a number between 2 and 30.
29.
29. I hate you. All right. So we have our absolute humidity up here. 0.029 lubs. All right. That's how many pounds of water is in there per pound of air. Boom. Now give me enthalpy, a number between, oh God, there's actually not that much room, between 55 and 60.
59.
57.
57, I heard 59. I'll go 58. God, I hate you guys. 58. You guys are monsters for creating a climate this terrible. Dude,
Yeah, I
what the-
live there.
Oh my
This
God.
is literally out. Oh wait.
58 BTU
Oh.
per lib.
It's literally outside of our comfort zone. Literally.
Literally. All right. So you see, I drew these 2 lines. Enthalpy on the top left to bottom right axis right there, and then absolute humidity on the x-axis. There's the intersection point. Woo! That's our climate right now. So you can go straight down to find dry bulb. Correct? Go straight
Yes, sir.
down. Find dry bulb. That's 105, 107, 107, 108 degrees.
And
Oh,
you
that's
said that's
awesome.
outside of our
Great
climate zone.
temperature.
Let's
That's
find.
That's
That's the
them
average temperature
Julys.
where I live. Come on, I literally live there.
All right. So now let's get absolute humidity or relative humidity. Got it. It's between 50 and 60, right around there. I'll just say 55, just to be nice. Relative humidity, 55%. It is at 55% capacity of how much water it can hold. All right. Okay, this one's going to be tough. Okay, not this one, but the next one. Let's look for dew point first. So you just remember, same absolute humidity, go to full saturation, and you go straight down, because at this humidity, at this temperature is when saturation is at 100%. That's when water starts condensing. Go straight down, Wablamio. 88. Dew point, 88 degrees Fahrenheit. Now, this is the problem. This is too dumb, y'all. Like it goes off the graph, so we can't even find wet bulb. I'm gonna have to improvise. Let's go.
Wait. It's too dumb. It goes off the psych chart.
Yeah, because the temperatures y'all gave me were like all over the place, you know?
Oh, they're too horrendous for the psych
Yeah,
chart.
see how it's like up here? This is not normal. So when you get a freaking temperature reading like that, it doesn't even care about that. So like you see how it just cuts off right there? Just
No, I don't even think it exists, the wet bulb, because if you would extend that line, the straight line right there on the top on the side of the graph, like extend it, I don't even think it would exist at that point.
Probably not. Yeah, now that I think about it, maybe it's like at boiling temperatures or something. I don't know. Whatever. So actually, I did this.
108 isn't boiling temperatures. In Celsius.
Wait. Oh. So, anyway, psychrometrics are pretty cool.
Is it because
Sorry, Bear, what was that? Did he just leave? Okay, that's not fun. Anyway, so
Man just said peace, y'all.
we're just gonna find the wet bulb temperature. We're just gonna go Wablamio to 100% saturation, and so this is the point where you can't add any more water. Go straight down, Wablamio. 91. 91 degrees Fahrenheit. That's
Well,
our
you know what,
temperature.
Edison? Now that we did a problem that doesn't exist on the chart, we at least were prepared for in case he gives us a problem that doesn't exist on the chart.
You see, I don't think he'll do that, but anyway, everyone understand? Everyone know why we went off the charts?
Yeah, for the wet bulb, that last one, it had to be off the chart, right? Because those angled lines don't hit the OG temperature. Or the
Yeah,
the
so you're
humidity.
adding humidity right now,
Okay.
and you're lowering the temperature, so you have to go off the graph. Beautiful. So hopefully everyone understands psychrometrics slightly better now.
So can I ask a question? It's like he's gonna give us two numbers, right? Just how like you given us, and we have to find the rest of the numbers using the chart. That's pretty much what
Probably, yeah.
every problem might be.
Yes.
Okay.
I
just
have a
using the chart.
high high suspicion that that's how our problems are going to go.
That makes sense. So it's kind of like the heating in degree cool days where he just gave us a bunch of them and we just kept on doing the formula, right? Pretty much same thing here. He's just going to give you two numbers out of the 6, find the rest of the 4.
That's what I am assuming.
We just
agree.
not though.
Can
Can
we just not?
though?
Oh, I'm dead. Oh, I'm dead.
All
Well, I
right.
mean, if he doesn't post it, then we don't have to do it.
No,
Hey, if
right,
no
right,
one
right.
tells him we don't have to do it.
I think people have already told him, but they didn't even respond to him. I
He's
never
going to post it at like freaking 3:50 or
On
something
Sunday.
on Monday. And it's like, okay, y'all have like an hour 10 to do it.
3:50
I
on
will
Monday.
roast
yeah.
this man alive if he does that.
Yeah, what did he do last time? He gave us like 30 minutes to do the problem.
Yeah.
No, that was Van Landingham.
No,
Yeah.
that was that.
That was Van Landingham, right?
Yeah, we're talking about Van Landingham.
Yeah.
This is his homework again. That's due Monday.
Brothers don't got no homework.
Wait, I
Yeah.
thought this was Clevis's homework.
No,
Mm-mm.
Klebis
Va-
is structural. Remember?
Van Landingham. Van
Oh.
on the ham is environment.
Yeah.
And then the
That's a nice
Kleb club is structural.
Exactly. So yeah, Klebis has no homework due currently, but Van Landingham does. Or he said we have homework and he never posted it. And we were supposed to do that right now, but now he didn't post it, so
Yeah.
we're screwed.
So if
Didn't
he
he say he
posted
was
it
gonna-
anytime on the weekend, you guys want to meet up anyways?
I mean, sure, I'm down to just meet up whenever. If he posts it, if he doesn't, sure, yeah, because
Wasn't
I-
he
I-
supposed to post it like an hour after class?
right,
Yeah.
yeah,
What if he's still coming up with problems?
no,
Bro, you just need a random number generator. You don't need.
yeah. Like you see how quickly Edison just said that. Okay, as long as you know 2 numbers, you can find the rest of the 4. That makes perfect sense to me.
Yeah, I mean, like,
Yeah.
unless you're trying to add Easter eggs into your problems, like what I did on number 4 right here. Unless you're trying to add Easter eggs, then it shouldn't take that long. Or wait, that's not the answer.
And so
Wait,
the
number three.
oh,
Unless you're trying to add Easter eggs to your problems.
Nice.
the basis of these problems is just using the chart and knowing which lines are where.
Go where?
Right.
And which
Yeah,
lines you
and it's
need to
like sort of
put
that
in.
intuitive thinking too.
Okay, and because they're labeled, I see that, okay, the wet bulb temperature is all these like slanted lines. I need to follow them. The saturation, I don't know, the relative humidity is all these curved lines. So I'm seeing, I'm trying to learn, okay, which line is which and which one.
So it's basically just tracing the line and figuring out exactly
Yeah.
where you are.
Okay.
So the real problem is just which lines do you use, you know?
And so the numbers you get are just where they intersect, where these intersections happen.
Yeah.
All right, because I thought we had to worry about, you know how you drew on the map, not on the map, on the chart, the warm summer day, the warm summer comfort, and then the winter, it was like in the middle.
Yeah, it was like
We don't need to worry about that.
here and
Yeah, we don't need to
here.
worry about that right now. You're thinking, right?
You might have to
Okay.
memorize them like later, just like where they are on the graph.
Yeah, probably. But as for like solving problems, it's not necessarily right.
No.
Okay.
I'm finally back. My
Hey,
Wi-Fi went
Hey,
out.
he's back, baby.
Wi-Fi went out.
yeah, I
Oh,
assume like
yeah.
you'll probably have a quiz for you like to memorize it, like the coordinates of the areas.
Or he's gonna say that he gives you the psych chart and all these words are gone. Like label which line is relative humidity, which one is
Mhm.
enthalpy.
Yeah.
Maybe.
All right. So we're
So what was
just gonna.
y'all's theory on the wet bulb? I was gonna say that it might be that dry bulb and wet bulb are literally the same because it's so hot that the wet bulb would just evaporate.
So I'm just gonna I'm just gonna do a quick review of what to do. All right. So first of all, finding your climate. This is usually just based on relative humidity or absolute humidity and your dry bulb temperature. Your dry bulb temperature is what you read on a regular thermometer. Relative humidity, you see how it's exponential because as you add more heat, it expands, the air expands, which allows it to hold more water. And that's why you see more and more absolute humidity temperatures being able to be plotted as the temperature goes up. So relative humidity, you see all these exponential graphs. This line right here is 100% relative humidity. You cannot physically add more water into it. You could raise the temperature, so you could add more water, but that would lower the relative humidity. 100% saturation. Cannot physically add more water in that at that temperature at that state. So dry bulb is your thermometer reading. Relative humidity, how much the percentage of how much water the air is currently able to physically hold. Absolute humidity, exactly how much water. It's a definite number, not a percentage. Wet bulb. So if you cool down a thermometer using water, like the water will sort of evaporate into the air and allow the thermometer to cool down. Water evaporates, thermometer cools down. So you add humidity by going up, and you go left by cooling it down. So you just see these faint lines until you reach 100% saturation, and then you go straight down to find your wet bulb temperature. Dew point, you're lowering the temperature with the same humidity until the climate reaches a point where it is at 100% saturation. If it's at 100% saturation, it is very easy for water to condensate because there's literally water everywhere. So you only lower the temperature until you reach that 100% saturation point, and you go straight down, you get your dew points. Enthalpy, it's sort of the amount of energy inside your air. It shares the same axis as wet bulb, but it's off slightly. I think one way that I like to think about it, this is probably not important at all, but if you think about it, you see how right here, enthalpy, right? There's your enthalpy line, but here's your wet bulb line. WBLMEO. So you see how during the same wet bulb line, you add more enthalpy. I was sort of thinking like, so you know the swing thermometers, you're swinging it, which means you're adding slightly more energy to it. You're not changing the temperature or the humidity like purposely. You're just spinning it around. You're adding slightly more energy to it, so the reaction of evaporation can take place. So that's why at the wet bulb temperature, it's slightly more, has more enthalpy, slightly more. At least that's the way I think about it. I might not be right, but you know, just bonus content. We all good?
Yeah, so that enthalpy line, it's the same slope pretty much as the wet bulb temperature.
Yeah.
Okay.
Enthalpy, wet bulb. Yep. All right. Hopefully y'all understood it slightly better today.
Yes.
I know, like, I know Van Landingham can sort of.
He showed us all those confusing psychrometric charts. He was like, let's look at all the confusing ones. I was like, why? Why?
I just got this one off of ASHRAE, the ASHRAE website. So
yeah, I like this one. It's clean. It's like drawing over it is what I like. We drew over it. It was very nice.
Okay. I think like doing it is better than like slides of you already have done it, you know?
Exactly. And he showed us those slides, and some of them were just obnoxious. Some of the charts. I was like,
yeah. It's like, I think you're like, if you do get into engineering / architecture, you're gonna have your own psychometric chart that like you reference. It's not like they're gonna give you one. It's like
Gonna be homemade.
Yeah, it's not like a standardized test. It's like, oh, you have to use this formula sheet. You can choose your own. It's the real world. Nobody cares as long as you're correct. All right.
I guess that's the good thing about it being open note, though, that you could choose whatever you need for your notes.
Yeah. I recommend this one off of ASHRAE. Like the PDF's protected, So what you're going to have to do is you're going to have to open the PDF, take a screenshot, and then use that screen cap and put in like Paint or something, and then save it.
Put it on an Illustrator, boy. Let's go.
No. So like, because it's protected, it won't open in Illustrator. I tried that.
Mhm. Not,
Yeah.
not even a screenshot?
Mm-mm. Well, you have to take the screenshot.
Oh, okay.
You like open it in a PDF viewer and then screenshot that boy. All right, so let's move on to structural, everyone's favorite part of Tech 2. All right, so we are going to look at the problems that Klebis went over just to get a better understanding of them. I got some Legos, so visual cues also help. So let's start, I guess. All right, so let's see here. I have my Word document up. I didn't take hand notes because I was a big dummy dumb. All right, so structural, where is, all right, bridge time. Y'all can still see Paint, right?
Yeah.
All right, so we have a bridge. All right, like, just as a side note, does everyone know why there's like this sort of hyperbolic shape? This
It's
or
a half
parabola.
pipe to skate on.
Yeah, well, it's not a half pipe. It's more of a hyperbola, parabola. Parabola.
I see half pipe.
This right here is about to be the 2.0 version.
This is half
Well,
pipe.
That's a perfect half pipe.
Actually, I'm just gonna.
That's my smile. What are you talking about?
This is parabola.
Parabola.
It's big U time. What you talking about?
So we have a bridge. All right, so we have a bridge. Does everyone like understand why it's a parabola?
Like, is this a graph, or what is this supposed to
Tension.
represent?
So it resembles the
Tension.
parabola graph. Like this is at its resting state what the cables would like sort of like settle into.
Okay, so this is just like an X and Y coordinate plane.
Yeah, sort of.
Oh, okay.
So like if you think about it, if you plot this on a graph, you know there'll be a parabola right there.
Yeah.
Obviously at that point, the parabola.
Okay.
All right, so we're just gonna go over this bridge real quick. I'm just gonna let's see, how do I want to do this? I'm gonna draw in blue. So we have a bridge, Blamio. And then we have the thingy in red. Yep, that's our cable that's holding our bridge. So if you think about it, there's like a bunch of cables holding this bridge together. Tension, yeah. Ooh. So the reason it's in this parabolic shape is at all points along this cable, I think like it's the tension force is like equal at all the cables or something. Just like something about like tension equilibrium. That's why it takes the parabolic shape. I'm too tired to think about that right now. I could explain it slightly more, I guess. No, I'm just gonna move on. All right, so Lablamio, we have, I just realized I made this way too long. All right, so we have a length. So we're just looking at the cable right now. We have a length of 2,300 feet. 2,300 feet right there. And then we have the height of the cable, I think. No, I'm just gonna simplify this. I'm just gonna, make this just reach the bottom of the bridge.
Hey, who's playing Super Mario? I heard that coin.
That's just notification sound. My phone broke, so I had to use my mother's phone, and that's her notification sound because it's very simple.
Dang, hope you get your phone. Hope you get a new phone fast, buddy.
I won't. Like, what's the point, you know? Not going out anytime soon. Anyway, so we have 377 feet. That's how high this bridge is. That's how high the cables, that's how high you have to worry about the cables for. Well, blamio. All right, so now we have some forces to think about. So we have a 13 KLF force all the way across here. I think this is how you notate it. I'm fairly certain this is how you notate it. Okay. Yeah, 13 KLF right here. 13 KLF. And what does KLF stand for?
Kips per pound foot.
Kips per linear foot.
Oh, Lord Farquaad.
Yes. So you have like your measurement. So you have like so you have your linear force right here. You can also have like a force across an area. So it would be K SF. So that'd be kips per square foot. So KLF, KSF. You know, you look at K and the F. That stands for kips and feet, and the L just stands for linear. So you know it's in one dimension. What else is there? All right, so that's all for the bridge. Now we have the deck, which is this bit right here. So this deck is, I'm just gonna write this down and gonna illustrate wide, 61 feet wide, 12 inches thick, and it is 150 pounds per cubic foot. So look here, P, F, pounds foot, pounds per cubic foot. It's volume. I assume there's also KCF, like KCF, kips per cubic foot, but that's a lot of pounds of force.
Nah, that's Kentucky Chicken Fried.
All right, so I'm just going to draw this deck. It's going to look terrible. So I can draw better by hand.
Sorry, could you say what deck is? What is the word?
So this is just the bridge. I'm just going to, so you see the cables right here.
Mm-hmm.
This is that thing right there.
Oh,
So this is what the bridge is made out of.
okay.
So I'm just gonna bam, 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 bam. Oh God. Oh gosh. Yep. Okay.
In IRL, that bridge would collapse. It's only 12 inches thick.
Yeah, it's like this much. Whatever. There's a math problem. So 61 feet wide. This is, remember, we take this measurement from here, 2,300 feet. And then bam, 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 blam, bam. That is 12 inches, or you could just put 1 foot. Right? Coolio. So now you have, all right. So now you have the bridge. You have the bridge dimensions. You have the deck dimensions, which make up the bridge. We're done now, right? No, we're not. So you also need cars to go over it, right? So those cars also weigh like a lot. So you need to think about the weight of the cars as well. So these are the next set of measurements he gives us. He labels this under traffic. So there's 6 lanes of traffic, and each lane is going to have 640 pounds per linear foot. So like if you just imagine a car and like a bunch of cars in a line, approximately every foot, there would be about 640 pounds of force per lane. So visual representation, you have a lane, you have 6 lanes. 1, 2, 3, 4, 5, 6. You have a bunch of cars, right? Bam, bam, bam. At full capacity, I guess, like during normal business hour. Each of these cars weighs a certain amount, and it averages out to 600 pounds per linear foot. So if it's 10 feet, you would get around 6,400 pounds if it was just a line of traffic.
So is it a single file line and just one lane, or is it supposed to be like 6 cars across the 6, like one in each?
No, this is just per lane. So you see right here, 640 pounds per linear foot per lane.
Gotcha.
Per lane. All right. Does everyone understand this traffic thing?
So the whole deck is going to be 640 times 6.
Yeah, per linear foot. But we'll get to that when we get to that. Coolio. All right, so we have all of these things. I'm just gonna keep the visual representations up. So we have, actually, why am I drawing it by hand? Beautiful boxes. 1, 2, 3. All right, so 6 lanes of traffic. And then we're only going to draw in 1 lane because this is per lane. This is a bunch of cars. And this is pushing down with a force. I can't really draw it down because this is the top view, but it's going inside. It's going inside. I don't really know how to represent that, but it's going to push down, not down, but like it's going to have a force of 640 pounds per linear foot in this 1 lane because it's per lane. All right, so now we got all the information. I'm just going to keep the visual representations up. And then, cool. Now we need to determine exactly what are we determining. I'm looking at my notes real quick. All right, so we're just going to do some basic stuff. We're going to find the weight of the entire bridge, Find the weight of the bridge. We're going to find the weight of the traffic. And then, are we not going to add this up? Okay, no, we're not going to add this up. Okay, yeah, all right, cool. So let's go full screen. And hopefully I'll remember everything. So we're just gonna plot a few vector points. One right there, we're gonna call it A. One right there, we're gonna call it B. Let's see, which one's a pin, which one's? Okay, so they're gonna both have, all right. So they're both gonna have reaction vectors because it's a cable. So it's gonna have a reaction vector in that direction. So you see how the cable is pulling down this way? It's going to have a reaction vector going in the opposite direction. Same thing over here. And because it's a cool parabola, both of these angles, theta, are the same. So remember back to day 1 when we separated vectors? We can do that here. So this is going to have a reaction right here. Reaction right here, and this elementary form of this reaction right here. Well, technically this reaction. So it's like tangent to that curve right there. Reaction right here, reaction right there. Everyone follow along. RXB, RYB. You have RXA, you have RYA. Cool. So now we need to just add a few more forces. So this is the weight of the deck, right? Now we need to add weight of wait. Okay, so this is the weight of the deck, or like all the surrounding bridge parts. This is the deck. This is the deck right here. We're gonna add this weight to this right here. I'm just gonna change this to a D real quick. Weight of the deck. So we're gonna calculate how much this weighs. All right. So it's just length times width times height. Easy stuff. That's 61 feet times 2.2300 feet times 1 feet. So that's the volume we have in cubic feet because we're foot times foot times foot. So that equals, I have my calculator. Bam, 61 times 2300 times 1, redundant. You have 100, 140, 300 feet, cubic feet. Don't write that down yet. I'm going to double check that. I don't know why he didn't just. Okay, this is dumb. Hold on. Give me a second. I'm just gonna.
Take your
Okay.
time, my brother.
All right. So this is how Van Landingham did it, which I think is dumb, by the way, but kind of makes sense when you think about it. So this is how Van Landingham did it, and why I think that's dumb. So you have the length. So what he's trying to do is he's trying to get a linear, a kips per linear foot measurement, sort of like how you got this measurement. So he's just going to use these measurements right here. He's not going to like bring this over and it's like, oh, this is how much it weighs. He's just going to just use these measurements solely first. So he's just going to get the area times the density to get the weight per linear foot. So if you think about it, he's going to take feet squared and he's going to multiply it by density, which is 1 over a force over feet cubed, or like a weight over feet cubed. So that's your density. So he's just going to multiply that out and he's just going to get a force per foot, right? So this is what he did. Area, 61. Now we're looking at a cross section of the bridge right there. So we're looking at a cross section right there. This is 1 foot. This is 61 feet. So you have 61 times 1 foot times 150 pounds per cubic foot, 150 pounds per cubic, oh God, that's not, pounds per cubic foot equals, and then you put that in your calculator, 61 times 1 times 150, 9,150. So you have 2 feet right here, and then you have a cubic foot, so that would simplify down to pounds per linear foot. So you went from pounds per cubic foot, multiply it by a length value, reduces it down to pounds per square feet. Multiply it by another length value, it goes down to pounds per linear foot. Does that make sense?
And this is the weight of the deck.
Yes. So we're calculating the weight of the deck right now.
So either we got 9,150 pounds per linear foot or 140,300.
So we're going to get to that real quick. So this is 9. We can simplify this because kips, one kip
Oh.
is 1,000 feet. So we can just divide this by 1,000. So you get 9.15 kips per linear feet. This is the same exact measurement. So just take a look at, so we're just going to take a look at this 61 feet. We're just going to break this down times 1 feet times 150 pounds per cubic feet, feet cubed. Does that make sense? I hope it does. So feet, that cancels out with feet, so that becomes feet squared. There's another foot measurement, so that cancels out, and that becomes just regular feet on the bottom, on the denominator. You multiply the coefficients, and then you just get 9,150 pounds per foot, or linear feet. I'm just gonna write this out.
Yeah, I like that you showed how everything like crosses out.
Yeah.
I remember that. Yeah.
I'm just gonna draw this in a different color. I know I'm taking a while, but hopefully it's worth it. 61 feet, that's 1, and then you have foot. So I'm just gonna draw in black the coefficients, and then draw in red the SI units, or just the measurements, what sort of units we're measuring in. So we have pound up here, and we have cubic feet right here. Cubic feet is just feet times feet times feet. So feet right here. So this is all being multiplied by together, so you can just treat it as like one sort of unit. So feet cancels out with feet. Feet cancels out with feet. And you're just left with pounds over feet, pounds per linear foot. And then you can just multiply 61 times 1 times 150 to get your 9,150 pounds per linear foot. Cool? Everyone understands this Klebus's way. I mean, yeah, Klebus way. So the reason he did this is, so later he's just going to convert this into a force by just multiplying it by the linear distance. But I think that's a little too much work. So what I'm going to do, and hopefully this turns out correctly, if this doesn't work out somehow, I'm just going to stop the recording and cry. Anyway, so wait. So we're just going to calculate the weight of the deck. How can we do that? We have a pounds per cubic foot, so we get a cubic foot measurement. 61 times 2,300 times 1, that's your volume, and then you multiply by the force per volume in terms of volume. So you have 61 times 2,300 feet times 1 foot. So you have 3 feet marks times 150 pounds per cubic foot. So this would just 61 times 2,300 times 1 times 150. You would receive, that's a big number. Maybe that's why he did that. You get 2. Okay, I think I understand why he did it. Okay, 2.104345 times 10 to the 7th. I think this is why he did it then. All right. So we're just not going to do that. Divide that by 1,000. Okay, I understand why. All right. So you end up with a total of 21.045. No. 21,045 kips.
And that's just the
Yeah.
weight of the deck.
That's the weight of the deck. I'm just gonna look at this thing real quick. Hmm. Wait, I'm so confused. Wait, sorry guys, this is gonna.
Nah, man, he had a big day today. Take it easy.
Oh, geez.
I'm trying to learn just as much as you, bro. So,
Yeah, where's the frick is? Did he just not use that? Oh, okay. Right. I don't think he uses this measurement. All right, let's see. Yeah, okay. So this is why he doesn't use the measurement. Okay. Yeah, this makes sense. All right, so remember when we were doing free body things, and so like we would have a pin, we have a roller right there. Bam, there's our free body diagram, right? We never really took into account the weight of the actual beam that we're doing work on, because that's what we're doing work on. It doesn't have anything to do with like with how the forces work out, because that's what we're doing the measurements on. So like if you like you take a Lego brick, it weighs like a single gram, but you don't really. But if you're like taking all the measurements, adding all the vectors together, then like you don't really need to worry about the weight of the Lego, I think. Jesus Christ. All right, I think we just don't need to worry about the weight of the deck. Oh my God, give me like 2 minutes to read over this real quick. Oh, I hate this. Okay, right. He never uses it. He never uses it again. Okay.
Yeah, that 9.15, right? That number is just nothing.
Yeah, he doesn't use it. Cool. Okay. All right. So this is just fun side quests. How much does the bridge weigh? Cool. That's how much it weighs. 21,045 kips, or 21,045,000 pounds. That's how much this deck weighs.
Right, but it doesn't factor in at all to the sum of forces in the y, x, or the moment at all.
Yeah, I don't see this number anywhere.
Yeah, I don't see it anywhere either. Now I think about it, he uses just like 2300, 13 KLF.
Yeah, I don't think he ever uses this like 61 measurement anymore. Oh gosh.
Yeah, that doesn't even appear, because we after this we just do right sum of forces and then x, y.
Yeah, so yeah, we're just gonna do sum of forces, but before we do that, let me just double check.
He played us, man.
He played us. What the frick? Hold on, does he not even use?
When will my professors teach me instead of just playing tricks on me, bro?
Okay, so it looks like he doesn't use this measurement either, this 6 lanes thing. So we're just gonna calculate this real quick. So we're just gonna calculate the weight of the traffic. So apparently he didn't use this either. So it's just we're just gonna calculate how much force the traffic would act upon the thing, upon the bridge. So just 6 lanes times 640 pounds per linear foot per lane. So the 6 lanes cancel, the lanes cancel out. So it's just 6 times 640. That's not 6 times 640. So you get just 3.84 kips per linear foot. I got 3,840 pounds per linear foot. I just change that to kips per linear foot. So it doesn't look like he uses this number at all. Let me just look through this real quick. Okay, he doesn't use this number at all. Maybe we'll use it later when he brings up this problem again. All right, so everyone got that, even though you probably don't need it for now?
Yeah.
All right, so this was like way too much. I think this is what kind of tripped people up. But now we're going back to something we're all used to, taking summations. Hopefully everyone's used to that, so this will be a breeze. All right, summation of forces in the x direction. That's not right. Why did I do that? I'm not trying limits. Summation of forces in the x direction, assuming right is positive. Let's set that equal to 0 equals, there's one right there, negative RXA because it's going left, plus RXB because it's going right. So RXA is equal to RXB. What a surprise. Whoa. Okay. So yeah. So what Klebas did in his is he drew both of the x vectors pointing right for some reason. Like it's not wrong, but it's slightly more confusing, I guess. In my opinion, might not be confusing for you, but anyway, RXA is equal to RXB. If you drew both of the vectors pointing in the same direction, it would be one positive, one of them is positive, one of them is negative. They're like inverses of each other. Well, not inverses. Reciprocals, I forget. One's positive, one's negative. But you see in this one, both of them are positive. So you have, it's going right positively, it's going left with a positive number. So it's like pulling with equal forces in both directions. If it was both of them going right, I know it's mirrored now. I looked at the recording, my camera's mirrored. So if both of them are going right, then you would be pulling with a positive force, and you'd be pushing with a negative force. So it'll be going the other way. So bam, small explanation. All right, so keep that in our backlog. And we're going to move on to summations of forces in the y direction. Equals 0 equals. So there are 3 forces, I think. There are 3 forces, right? So we have an RYA here and an RYB here. They're both going up, which means they're both
Positive.
Positive. RYA plus RYB. And then now we have this force right here, this 13 kips per linear foot. Now, so we have to add that to the equation, but first off, is this going to be positive or negative?
Negative, right? Because it's going down.
It's going down. So it's going to be minus 13 KLF. Now, we have to convert this into a force vector. We can't use it in its current state because it's kips per linear foot. It's not kips, we need kips. So what do we multiply by? We multiply it by a foot value. 2,300 feet, 2,300 feet. So that turns this kips per linear foot into a kip, right? This cancels out. This foot mark cancels out with this. So it's just 13 kips times 2,300. So we're just going to do that real quick. I'm just going to move this to the right side, our left side, RYA plus RYB. And this is going to switch from negative to positive. So it's positive 13 times 2300 to 29,900 pounds or kips. Oh my God, that is a huge number. 29,900. Let me double check that real quick. Yep. 29,900 kips. So this entire thing is this 30,000 kips of force, and both of these cables are reacting in the opposite direction with 30,000 kips total. We don't know exactly how much each one is pulling. Hint, it's going to be equal, but we don't know how much it's going to be pulling. So this is another unknown. So I'm just going to put this also in our backlog. RYA plus RYB is equal to 29,900 kips. Beautiful. Let's do moments right now. Yes, we're doing moments. All right, moments. Summation of moments, and then we're going to go counterclockwise is positive. So where should we take the moments? Should we take them at A or B or somewhere else?
So we need to take it where like the least work is needed. I'm thinking B, but I don't know if that's the right answer.
It doesn't matter where you take the forces, but yes, you can take into consideration like the least amount of work that you have to do. But yeah, we can take it at A or B. Clavis took it at A. I'm gonna take it at B because I'm a rebel.
Okay.
All right, 0. So we have 5 forces. We have RXA, RYA, RYB, RXB, and this 13 KLF right here, correct?
Mm-hmm.
So we're taking the forces at this point right here, B. This is pretty easy, honestly. So you see this RYB vector going straight through B, distance of 0. RXB going straight through B, distance of 0. RXA is also going straight through B, distance of 0. The only 2 forces that we have to worry about are the 13 KLF and RYA over here. So I'll just start off with this RYA. RYA times how far is it away from B?
2,300.
2,300. Beautiful.
Yeah.
So remember, it's a force times a distance to get a moment. So if you like did the black hole thing, see how it orbits around B, that radius right here is 2,300. Beautiful. And then let's take
Wait, so it's positive because it's going counterclock.
frick. Okay, it's
Negative, isn't it? Because it's going clockwise.
Yeah, I forgot about that.
You're good. Clockwise is negative. Yeah.
Clockwise is in fact negative. Let me just double check this real quick with the notes I took. All right, cool. This is gonna work. All right. So now we have our 13 kips, right? Plus, oh wait, well, we don't know what it is. Haha, gotcha. 13 kips of 13 KLF. 13 KLF times, all right. So now we need to, oh God, oh my God, I'm so sorry. Okay, KLF. Now we need to convert it into a force because right now it's force per distance, force over distance. We need to convert it to force first. Kips per linear foot. What is the total span? 2,300 feet. 2,300 feet. This is how much force is right there. This is how much force this KLF thing is outputting right now in this free body diagram. So now we have a force, but we need a moment, and moment is a force times a distance. So how far away is this force from B?
So now we have to do the middle of the line load, right?
Mm-hmm.
Only. So that means it's half of 2300.
Half of 2300.
Oh, okay.
So you take the average like area that the force is taking. So let's say you have, let's say you have a Lego. Let's say you have a Lego. So it has a consistent kips per linear foot. Let's say each of these bricks is 1 linear foot. Each of these bricks is 1 linear foot. 1, 2, 3. Get that last one. 4. So you have four measurements of kips per linear foot, and you have 4 of those linear foot. So it's going to be like 4 kips essentially. So we're just assuming each of these bricks is one kip, and this is like 1 kip per linear foot. So you have these 4 bricks, and if I balance it on my finger, if I do it correctly, if I balance it on my finger, it should balance on that midpoint right there, right in the midpoint. That's where the average amount of force is going to be at. Does that make sense?
Right.
All right. Told
Because
you.
like, yeah, it would be silly to like say like, oh, you know, either or. Like it had to be right in the middle. It makes the most sense.
Have to be right in the middle.
So
I said I was going to grab Legos.
I love the analogy. I liked it.
Yeah. So we're going to multiply it by half of 2300. 2300.
What is it? 1,150, right?
Yeah, 1,150.
Okay.
1,150. That looks terrible, but we're just gonna. Oh yeah, positive or negative.
So now, if it's in the middle, and it's going down, and then it's gonna circle like this counterclockwise. That's positive, right?
It's positive. Beautiful. So it's like it's already down here, but if we like step it back a little and like
draw the yeah, dude, Edison. Ever since we did that, I always draw the little vortex, the black hole.
Yeah,
I like that.
If I become a math teacher, I will use that.
That is very good.
All right, beautiful. Plus. All right, RYA. I'm just gonna move that to the other side, and we're just gonna do some quick maths right now. So RYA is on the other side. So we have 13 times 2300 times 1150 divided by 2300, because that's what RYA is multiplied by. We have to divide by 2300 feet in order to get RYA by itself. So divide that by 2300 and we get 14,950 kip feet. Yes? We just multiplied this, and this to get a number, and then we divide that by this to get the same, to get this answer. Everyone understand?
Yeah.
Cool.
So
wait,
we
frick.
have...
No.
Oh,
Kip,
what?
just regular kip, just regular kip. I'm so dumb. Oh my god. Just regular kip, frick.
Oh yeah, it's a force.
It's a force. Oh my gosh.
It's a force.
I feel like Clevis now.
Fair criticism. God damn.
Okay. To be fair, I didn't look back at the answer sheet. If I looked back sooner, I would have caught it. All right. So it's a force vector, so it's in kips. Hope no one is writing in pen. Oh my god, this is going so downhill. All right. RYA, 14,950 kip. So that's for this one. 14,950 kip. I'm gonna type this out. 14, 950 kip. Go in the up direction. Cool. Now we can just plug that into this boyo.
But in reality, it's just you've already given us the hint that it would be the same.
Yeah. So if you did plug it into that boyo, it would just be RYB equals 29,900 minus RYA, and you know,
Which is 14,950, and it is exactly half. I'm just looking at it
sir.
right now.
Yeah, divide minus. Where's my minus? Minus 14,950. Get the exact same thing. RYB is the same thing as that. So 14. I'm just gonna type this out again. 14,950 kip is equal to RYB, both pointing up. Those add up to 29,900 kips. And then this KLF force pointing down, that is also 29,900 kips. So those cancel each other out and we're in equilibrium. Cool. What's next?
So now that's what I was thinking. I was like, now we still have RXA equals RXB. Now I'm thinking, I don't know. What,
All right, so we're gonna cut it real quick. We're gonna take internal forces. Remember internal forces that we learned about?
right. You got to slice the bridge in half.
We
Right?
gotta slice the bridge in half. This is what we're gonna do.
That's what you have to do.
All right, so I'm just gonna get rid of this traffic stuff and this stuff right here, real quick like, and then I'm just gonna minimize this. Just like make this a smaller boy. So it's still there, and we're gonna cut it in half. So we isolate an RXB or an RXA. We're just gonna do RXB because I don't want to think right now, and that's what Clubus did. Okay, RXB. Okay. So now the question is, why are we cutting it right at the midpoint? Does anyone know why?
I know he said it. I think it's because like that line is going straight down at the middle.
Mm-hmm. So you know cables. Let's say you have a cable right here. You have a cable right here, and it's getting pulled this way. It's going to have a reaction force opposite of which way it's being pulled. You don't know the angle. That's the problem. But you know it's going in the opposite direction. You have a cable that's going like here. Reaction force in the opposite direction. So the same concept here. So we have a reaction force somewhere along the cable, but we want to know we want to like calibrate that. So a good calibration point is when the slope is equal to 0, when this is completely flat, when it's changing from going down to going up, from right to left, or going down to going up from left to right. So we're just going to take it at that because the reaction force, or I guess the internal force right here, is going to be, which way does he draw it? I think he draws it this way. So that's our axial. That is, hold on. Let me just make sure. All right, this is our axial force, right? That's going to be a P for parallel. There's going to be a shear force right here. The V for, I guess, looks like scissors. And there's going to be a moment reaction as well. And that's going to be an M. Right, so like remember, when we're taking summation of moments, we take summation of forces in the X direction, summation of forces in the Y direction, and summation of moments. This is like the exact same thing. So it's just the same 3 measurements to define a part of a body. Cool, so we only care about the All right, we only care about the axial force right here. All right, we only care about the axial force, and I'm just going to simplify this. Instead of just calling it axial force, shear force, and moment force reaction, I'm just going to call it a tension reaction. I think that's, yeah, in cables, because like they're just a line, so there's only a tension reaction. So yeah, tension, we're just going to call this tension reaction, and then we're going to label this C. This is going to be B. So I guess it's sort of like internal forces, but because it's a cable, it can only like go in one direction. We're just going to call it tension. All right. Coolio. So we're still going to have all our forces right here. Still going to have our kips per linear foot right here. So we're going to have our kips per linear foot, and then 13 KLF. And how long is this? This is 2300 divided by 2, because we cut it straight in half. So that's just, my internet connection is unstable, whatever. That's 2300 divided by 2. That's just 1,150 feet right there. And this is still 377 feet. All right, so we're just gonna do the same things, I believe. All right, so we're just gonna take the summation of forces in the x direction and the moments. So we already know what RYB is right here. We solved that earlier. We already know what this is. So this is 14,950 kips. I'm just going to copy that. Going to move that over here. That's 14,950 kips. So we don't know what RXB is. So this is currently what we're trying to find out. Yeah, we don't know what we don't know what the frick that is. So we are going to take a summation of forces in the x direction. Summation, that looks terrible, sigma. Summation of forces in the x direction, assuming right is positive. To set that equal to 0 equals, there's an RXB going right, positive. There's this T, this tension reaction. I'm just going to call that TC because it's at point C. We named that C, minus TC. So TC is equal to RXB. I forgot to write B. That's another equation that we're just going to put in our backlog. TC is equal to RXB. Woo. Now we're just going to take summation of moments, and we don't need to take summation of forces in the y direction because we already know all the y direction, all the y forces, what they are. RYB, 13 KLF, bam, we're good. All right, so summation of moments, we're going to take them at, what did the clubist take them at? We're going to take them at B. Right, this makes sense. Why do we take it at B?
Because all those forces cancel each other out, or there's 0. My bad. They don't cancel each other, but there's 0. Like RYB 0, RXB 0.
Mm-hmm. Yeah. So you see this tension force, this KLF force, RXB force, RYB force. You see how they intersect right there, the RYB and RXB. So they're going to be a distance of 0. So we took 2 terms out. So we're pretty Gucci. All right. So we're going to start off with the 13 KLF. 13 KLF. Now remember, we're trying to take moments, so we need a force times a distance. Right now, KLF is a force divided by a distance. force per distance. So we're just going to divide by how long that is. How long is that?
Wait, what? 15, 11, 50, I mean, 1,150.
Yeah. So 13 KLF times 1,150 feet. So now we have the total force. Now we need another distance, defining how far it is away from B. So how far is that away from B?
Half of that.
Half of this, because that is the average force vector. So it's just 575 feet. Now is that positive or negative?
Counterclockwise, so it's gonna go down and then curve upwards. So that's counterclockwise.
Counterclockwise, that's going to be positive.
Positive.
Cool. And now we have this TC, this tension reaction. Tension at C. How far away is that from B?
1,150.
Okay,
Wait.
I'm leaving. Y'all have a good night.
All right,
Thank
take
you.
care.
Thanks for coming, Ali G.
Hope it was helpful.
Wait. You're right, Edison. You're right. My bad. It should be 377, huh?
Yeah, 377 feet.
Yeah, because now I remember where the arrow's going that way.
Yeah.
Yeah.
So see how it actually shouldn't be drawing it like that. Should be drawing it like this.
Yeah. Okay.
So if this is the radius right here, so that's how far away it is.
Right.
Cool.
So that's going clockwise. That's negative.
Clockwise, negative. Beautiful. We're just going to put TC on the other side. Just going to do a bunch of math. 13 times 1150 times 575. So that's this KLF force right here. That's the moment. Divided by 377, because we put this to the other side, and we're just going to divide by 377 to get the tension reaction force by itself. We end up with, let me double check this real quick. Yep, 22,801.7. What unit are we using?
Okay, moment. So it's a KLF.
So we solved, so this is going to be TC, tension at point C. What would this be? Would this be a kip, a foot, kip feet?
A kip. Maybe
A kip, there we go, yeah.
Just a kip, because it's just a force.
Yeah, it's just a force. So you just look back, it's like, oh, it's just a force going that way.
Yeah.
So you see right here, we have KLF times foot. So this becomes kip feet. And this is an unknown times feet, right? So we
Right.
divide, so once this is on the other side, we divide by the feet. We just left with kip.
Yes. And even if we didn't like write those out, just remember it's a force.
Yes.
It has to be just like kip.
Yeah. So 22 kips. So we're just going to take this back up there. We can use that in our backlog. RXB is equal to 22,801 kips. 0.7. Cool. Now we know RXB. What's RXA? Oh wow, this thing that we first came up with in the very beginning. RXA is equal to RXB, which is just 22,801.7 kip. Cool. I think that's it.
So now we know all of those. We know RYB and all of that.
Yeah. But you know what? Let's take it a step further. Don't worry, this is still what Clevis did. So.
Wait, what are we missing now though? Now I'm trying to think. What
we have RYB, RXB. What can you create from RYB and RXB?
B or
RB. just RB and RA.
Yeah.
You have
The reaction itself, not its component.
yeah.
Okay.
So you have the components. Now you create the reaction. And did he solve for the angle too? He didn't solve for the angle. Huh. So we're just going to solve for RY or RX, RB. Okay. RB. RB. So how do we solve for that? It's just RB squared is equal to RXB squared plus RYB squared. Pythagorean theorem, RB is equal to this boy squared, and then RYB is let's see, where is it? RYB, RYB is this boy squared. So we're going to take the square root of, I'm not even going to write this out because we're almost there, and my batteries are low on my headphones. So square root of RXB, which is
22,801, right?
801, yep.
22,801
squared plus RYB,
which is
it's kind of hard to find.
14, right?
Yeah, the 14,950.
Oh, they're the same. Okay, yeah. Plus 14,950 squared. Take the square root of all of that, and you get RB equals.
And I ended up with 27,265.7 kips. Make sense?
Sir, and so that's the reaction in the. Wait a second. If they're the same, then it has to be the same on the other side.
Mm-hmm. So our RA, but we don't really have a formula for that. So we're gonna have to do it the hard way. Gonna have to do it. I'm just kidding.
I'm dead.
We're not even gonna solve for RA.
Right, but it is the same number, right?
Yeah, it should be the same number.
Okay.
And then I guess you can also find the angle. I guess.
Yeah. The angle of what the ends of the parabola are going at, right?
Yeah. So this is just so remember how the parabola is always, the slope is always changing. At this moment, what is the slope of the parabola? Because, at this moment, the slope of the parabola is 0.
Mm-hmm.
Was at this moment. Sort of a little calculus mindset, but,
Yeah, so then we have everything.
Yeah, you have everything. We can just take the inverse tangent. So this is going to be theta. This is going to equal inverse tangent
of just that number, 27.
Of no. We're going to take RX RYB.
Oh yeah, opposite over adjacent, right?
Yeah, RYB over RXA, and you just I'm just gonna do it right here. Inverse tangent RYB is 14,950 divided by
22,801, right?
22,801. Sorry, I'm a little slow. And then you just get 30. That doesn't look right.
Are you in degrees?
Oh, I guess it is like that. So you get 33.25 degrees. So this drawing is actually not to scale. To see how I made that sort of angle. It's actually more of the shape is more of a this.
And this is the angle, where's the theta? Can you draw where the angle is?
So this is getting super colorful. So that's theta right there.
Oh, okay. Thank you. I needed that.
All right.
That makes a lot of sense.
But this is not to scale. So yeah, this sort of makes sense.
Yeah, but I see where theta is now. Okay.
Yeah. All right. So this is way too much.
No, Edison, thank you. I don't even know how to say thank you. I don't know.
Edison, my guy.
So
Party time.
hey, I saw those. That's
fun.
why I'm
That is-
like,
that is lit.
dang, bro.
That is lit.
Yes,
And you know
sir.
what? I can control it all from a phone.
Is it,
Hey.
wait, is it one of those bulbs where like you can control the light from your phone, bro? That's it. I'm going to Home Depot this Saturday and I'm buying that. I'm ready to buy that now.
Boom.
That is so cool, dude. I want
That's
to buy
pretty
it.
nice.
And
It's
it's just
nice.
a bulb, right? It's just the
Yeah,
bulb.
just a bulb, and it runs
is-
off the Wi-Fi of my house.
That is so cool. I am buying that bulb from Home Depot. I seen it and I want to buy it now that I've seen you use it.
Oh, I've had this bulb for over 3 years already. I've had it since high school.
Right. I've seen it at Home Depot, right? And I have a regular old bulb, but I'm gonna buy the colorful bulb because I like color too. As well.
Dude, the only reason why I got this bulb was because I have a lamp on the other side of my room to light up like my whole room.
Mm-hmm.
So I can turn off this one with my hand if I wanted to. But that one I would have to get up out of bed, go turn it off here. So this time I could just plug my phone in the charge. Don't even have to touch a lamp and just
I love that. I love that. That's
the
really
amount of work that went into getting these two bulbs just to be this little bit much more lazy. But it's worth it.
All right.
Edison, thank you so much again for taking.
Yeah, thank
the
you,
time.
Edison. You deserve a party, man.
You deserve a salary.
A pizza party.
Pizza party.
Oh,
Yo, Ali had some pizza. Let's grab some of that.
Ice cream.
No, Ali was denying us pizza earlier.
oh no,
I'll remember that.
it's okay. Edison did not deny us knowledge. That's what matters.
Mhm.
That is very true.
Pink's Pizza.
Yeah. All right. So, everyone, we ready to move on to the last question of the night?
All right.
All right. Beautiful.
Comfort, reading, energy. There we go.
All right. So, I'm gonna make a building now.
If I randomly disconnect, it's because my laptop died.
Okay. If I randomly mute, that means my headset died. So,
I got you.
yeah, I'm getting the low battery notification on this.
If anything randomly happens to me, it was my cat. He jumped on my laptop.
I think my computer should survive.
We're all having problems, and Emron's like, "Yeah, I'll be fine."
I think my computer will live.
All
My
right.
cat was
So,
fighting me earlier last problem. I couldn't really get a good grip on it. I was just like, ah. I finally fell asleep again. Must be nice.
So here we're just drawing the building, right?
this is the building that that Clavis did.
Yeah,
It's a domino.
it really was a domino. Yeah.
So this was. I'm just gonna draw this real quick.
Yeah. I need to look back at the numbers. Are you using the same numbers as him?
Yeah, I'll use the same numbers just so I can just follow along.
No, I agree. So the top half was what, 10 feet.
Yeah, 10 feet.
The bottom half is 12 feet.
And then it's 30 feet wide.
Yes, sir. Wide.
Yeah, if I was not so tired and if I cared more, if more people showed up, I'm just kidding. I probably would have made different problems. Use different numbers, maybe make it my own problem. I don't know.
I think people were really hoping that Van Lanningham would just post the homework, and that's what we were doing.
Yeah.
But he played us all on that one.
Yeah.
He plays us like a fiddle, guys.
I'm really gonna be upset as if he sends it to us like Sunday or something. I'm gonna be pretty pissed. I don't know. I'll do it, but I'll do it angrily.
You're one of the questions you're gonna misspell it and says this question was done angrily.
Yeah.
So
And then 5 kips in the middle. Yeah. That's what it was?
5 kips per linear foot, KLF.
KLF. Damn it. Whoa. So it's different, huh? We got 20 kips on top, and then you have 5 KLF as a line load.
Yeah, 5 KLF. Yeah, linear load.
Oh, I have. See,
Yeah,
I already
that's the term I was
misnumbered.
looking for. That's the term I was looking for, linear load.
Building, right?
Hmm?
This is kind of like based off that building that he did. Like
Yeah,
he
this is his building that he did.
Yeah, this is the building, the one he did.
So now you just have
But see, my notes are all messy because he's a head ass, dude. Fucking
Yeah.
play this.
It's being recorded. Who cares, honestly?
It's being recorded. Yeah, my bad.
Whatever.
They'll
Anyways.
know the real me, bro.
Need a Minecraft session after this guy.
I'm too tired for Minecraft. I'm so sorry, man.
No, I feel you. I'm sleepy too.
Yeah. I also need to eat dinner after this.
Yeah,
That's
yeah.
per usual.
Yes, sir. We'll finish this up and then we'll all get pizza.
Yeah. All right.
I'll send you a long distance pizza. I'll order it and put it to your address.
Oh.
All right. So
That's it for labeling the building, right?
yes, sir. So this is what I want to get my blocks for. So
There in the middle.
all right. So it's 12 feet. And that's 10 feet. So all right. So we have our building, right? We have our building right here. I'm just gonna add a floor to it because why the heck's not? We have a building right there, right? There's a little human right there. There's a human right there. So this is going to be a linear force right here, and then there's going to be just a regular force right there, 20 kips.
And then there were 3.
So that's our 20 kips. And then we have our 5 kips per linear foot. Oh gosh, 5 kips per linear foot down here. So we can just represent that by just like every single foot, quote unquote, we're going to add a few bits of force. So now we have that, and we have that. That's essentially our free body diagram right there. Cool.
I like the 3D FBD.
Yeah.
Not gonna lie.
All right. So right now we are going to start at the roof. All right. So make this A, gonna make this B, gonna make this C. A, B, C. I'm not even gonna label it. So this is the midpoint, 15 feet. A to B is 15 feet. B to C is 15 feet. I'm not just gonna draw that. All right. So we're just gonna take this section right here. Just gonna take that. So this is what we're doing to our thing right now. We're taking this right off the top, right? But we need to label the pins and the roller. So what I'm gonna do is I'm gonna use the roller. We're gonna use the pin as red. We use the red pin, yellow roller. So we have our pin and our roller, and there's our load, right? So we're just going to diagram that real quick. So we have that. We have our pin on the left side, right? This is showing this is on left side, right?
Yeah. Like
okay.
Red is in the triangle. Yeah.
Okay. So I'm just gonna color code that as well. Oh my God. Stop.
Yeah. So the red block is the triangle, right? The pin.
Yeah.
Yeah.
The red block is pin, and then the yellow
is roller.
Is your roller. Okay.
Gotcha. Okay.
So remember, we just took this off the top of the thing, and then just to hold it together, we just showed this is a pin, this is a roller, and there's our load. Cool. So we have our reaction forces. I'm just going to draw these in black. We have our X reaction force right here. This is C, B, A, X, bam. I mean, they could be going in the opposite directions. I'm just going to point them at it. I think this is what we did normally. A, B, C, right? And then we have the 20 kips right there. Cool, this is going to be very simple.
Way to go, cut up. Way to go, cut up.
Let's see. Wait, no, frick. God damn it. This is not horizontal. This is vertical. This is vertical. I'm making so many mistakes right now. This is vertical. Man.
Okay, mate. We're all tired here.
Yeah.
It's Friday. Tomorrow's weekend day.
Yeah. So we have RYA right here, RXA right here, and RYC right here. We also have the 20 kips. So that's our four moments. I mean, four forces right now. So, right. So it looks like Clubus doesn't really care about. All right. So this is what Clubus did. We're just going to take the moment at A. We're just going to take the summation of moments at A. Because I guess,
yeah, because you take out those two forces. All right, yeah, that makes sense.
Yeah, at A. So these forces don't count.
The only thing that matters is the 20 kip and then the C, RYC.
Yeah. So we have 0 equals 20 kips. How far away is that?
15.
15 feet. And then is it positive or negative?
So it's going down counterclockwise positive. Wait, no. My
Looking
bad.
at A.
At A. So it's going clockwise negative.
Negative. And then we have this one. Is it going positive or negative? Right here.
This one's going counterclockwise.
Yeah. So RYC. And then this is how far away is this? Just
15, right? No, 30.
30, correct.
My bad.
30 feet. So now just RYC. Do that to the other side. Just do some quick analysis. 10 kips. Yeah, 10 kips. All right. So now we need to find. We're going to find the bending moment at B right now. We're going to see how much it's bending right here. How much, like, I guess, stress is the beam taking, like, right at the midpoint right there. So we're going to cut it in half. So we have this boy, and I can't cut this in half, so I'm just going to cover this half. Right. Just going to cover this half. So we're just going to take the side with the roller. Just make sure.
So now the pin's gone away.
Yeah, so we're just going to cut this in half. So we're just going to be left with this roller right here, 20 kip right here, going straight down. Have this going up. This is our 10 kips from RYC, 10 kips. And then we're going to figure out the moment. We're going to find the bending moment right here.
At point B, right?
Yeah. At point B. So this is MB. So now, I'm just going to take the moments at B, counterclockwise, obviously. So we have B, of course. So this is already a moment, correct?
Oh yeah. It's right there.
Yeah. So we're going to take summation of moments. We can either take actual moments or we can take forces times the distance. So we have three things right here. We have two forces and we have a moment. So for the moment, we can just take it right there, MB, this is going counterclockwise, so it's positive. We have this force, 20 kips, it's 0 feet away. It's pointing straight at B right there. So it's just going to be
nothing.
times 0, nothing. And then and then plus this 10 kips right here. Plus this 10 kips, it's going up. It's going to go counterclockwise. It's 15 feet away from B, 15 feet. MB is equal to minus 150 kip feet. So that's how much force is, that's how much bending force is being taken right there.
Yeah, the bending moment at point B.
Yeah. So if you think about, let's say this is your beam, how much it can bend like this before it just breaks, you know? Yeah, I think this is how it works.
Yeah, the bending moment at point B. So like.
Yeah, so
if
this
you
is,
think- Oh yeah.
so yeah, this is, so this is your beam. It's just gonna bend right there, right?
Right. So if you give it more than 150 kips per foot.
Yeah, so right there. Oh gosh.
Oh
See,
yeah,
that's
and
one.
you're right, because you had the full 30-foot thing, but then you remembered it's only 15, right?
Yeah. So this is
Yeah.
what we did when we cut it in half.
Yeah.
And then, so yeah, that's how it would look like. So remember, like this force right here, this bending moment, it isn't caused by this force right here. It isn't caused by this force. It's caused by the reaction of these forces. So if you just had this force right here, it wouldn't go, it wouldn't do anything. You would just push it down. But because you have the columns right here, it's gonna bend a little because of the reaction force that's pushing up right here.
Oh, okay. So if it was just like the beam floating in space, right, with no columns, then it wouldn't make sense. But because of the RYC and RYA,
Yeah.
right?
So it's gonna push back.
Yeah.
So it's not directly affected by this. This isn't the direct cause. It's because these two columns push back.
Against the 20 kip.
Yeah.
Coming
So
down.
like another way you can look at it is see, it's pushing down with the kips.
Mm-hmm.
It's not going to do anything. You have the two columns. It's going to bend it right there,
That
right
was,
in the middle.
That is so good.
Right in the middle. You can see
Yeah.
there's a little bend right there. Bendy.
Like that a lot.
So yeah, that's your moments. Cool. So now we need to know that this beam right here needs to be graded for to take at least 150 kip feet of moment of bend.
Right. Otherwise, the beam will break.
Yeah.
Okay.
If the beam is at 149 kip feet, then it'll break because 150 is over 149, and that's not its threshold. So yeah.
Okay.
So we're good with the roof. Now we're just going to do the exact same thing with this floor slab right here.
Yeah, the second floor, right?
Yeah, it's literally the same thing. So we're just going to do D, E, F. There's a pin, there's a roller, I think. We had a pin and a roller. Did the clevis add? Yep. A pin and a roller. Five KLF. That's 15 feet. 15 feet. So there's a reaction right there, and a reaction right there. Very sloppy, but I'm getting tired.
You're good.
All right, so I believe we're just going to do literally the exact same thing. Yeah, all right. So remember what we did in the first one? We're just going to take the moments, the summation of moments at this point we're going to call D. This is going to be E. This is going to be F. Definitely. Right. Summation of moments at D. That's a B. Oh my God. Counterclockwise equals. We're going to set that equal to 0. And there's this reaction vector right here, RYF. And that's going to be positive because it's going counterclockwise. And we have this 5 KLF. So we have this 5 KLF. So that's a linear load. So we're going to have to multiply by a distance. Wait, oh my God, frick. Okay. Scratch that, scratch that, scratch that. Oh God. So we're going to have the RYF, right? RYF, how far is it away from D?
30 feet.
30 feet away from D. And it's going to be positive because it's going counterclockwise. So we have, that's a moment. We have a force times the distance. So now we have this 5 KLF. It's going in the down direction. It's going to go clockwise around D, so that's going to be negative. So it's spread across 30 feet, right? This 5 KLF. So it's going to be 30 across 30 feet. So this is your force. Now you need to multiply by distance. How far is it away from D? You just take the average. You just take the average. You just take the middle right there. So it's just going to be 15 feet. 30 times 15 feet. Just double checking. So it should be 5 times, yeah. So RYF is equal to 75 kips. Well, that's 75 kips going up. Cool. Now we're going to do the exact same thing because we want to know the bending moment at E. Yeah. So we're just going to find the bending moment at E. Dude. Just going to move this up. Jeez. 5 KLF. So now we're just gonna take this frick. So we're just gonna cut that in half right there. Gonna look at this side. So we have E, we have F, that's the roller. So we're trying to find the bending moment right here at E. We still have the 5 KLF right here. That hasn't gone away. So summation of moments at E, assuming counterclockwise is negative, we have this ME right here.
Yeah, Carlo. Yeah.
This moment right here, it's always going counterclockwise, so it's positive. And we have this 5 KLF right here, 5 KLF. Linear load, we have to convert it into a force or just a normal load. So how far is this stretching? We cut it in half, so it's just going to be 15 feet. 15 feet, spanning across 15 feet. And then we have to add a distance. How far is it away from E? Take the midpoint, 15 divided by 5 is 7.5 feet. Positive or negative, it's just going to be negative. Because it's going down, it's going to go clockwise, down clockwise. Woo. ME is equal to
ME?
Yeah, because we're taking the moment at E.
Right. But did you already do the 75 kips times 15?
Yeah, we're just going to do that real quick right now. We're just going to do ME equals 5 times 15 pi 7.5.
Oh yeah, because it's 5 times 15 is 75. Then 75 times 15. Yeah, you're good. You're good.
Yeah. All right, and that's just going to be 562.5 kip feet.
Yes, sir. Yes, sir. And that is the moment at E.
Yeah,
There you go.
563. 563 kip feet.
Nice. So we found the bending moment at B, and now we also found just the moment at E.
It's also a bending moment. It's the same
Oh, it's
thing.
another. Oh, it's the same thing.
Because remember, we're cutting it in half, and we're taking the internal forces.
Right. The PV and M.
Yeah,
Got you. Okay.
the PV and M. Yeah. So 563. So, and if you remember, this one was negative 150 kip feet. So if you look up here, you have 150 kip feet, but down here on the second floor slab, you have 563 kip feet. That's almost 4 times the bending moment at B. So it's going to be around like 4 times stronger. It has to be 4 times stronger in order to support this 5 KLF load.
Yeah.
Does that make sense?
And that's what he was saying. Like, if you start stacking stuff, right? Like, obviously, the beams lower are gonna have to deal with more.
Well, that's in the column. That's when we're talking about columns.
Oh shoot. Okay.
But it's just dependent on what sort of forces right here. So you see the 20 kips.
Mm-hmm.
It's just 20 kips, but you see this 5 KLF. It's spread across 30 feet. So it would be 5 times 30, 600 kips, I think. No, 150 kips, crap. So 5 times 30 feet, it'd be 150 kips compared to this 20 kips, you know?
Oh, okay.
So it's just that sort of, this is a lot more than that. All right, so cool, we found that stuff.
Gotcha.
All right, I'm so tired. Let's do this last one. We're gonna look at the columns. Yep. We're gonna look at the columns. So I'm just gonna look at this real quick. We're just gonna look at this baby.
Is this the maximum axial force? Is that what you're talking about?
I think axial. Yes, axial.
Okay.
So we're just going to look at this column right here. So we're just going to draw that out real quick. So we have this column right here. And we have point A, point B, and let's just call this G. This is F right there. Call this G. So this is 12 feet, 10 feet. So remember how much this force was? This was 20 kips.
Mm-hmm.
So it's going to push down with 20 kips. So that means it's going to be spread evenly. The reaction force is going to be spread evenly across both of these because, you know, the force is right in the center. So it would spread out evenly to the columns. See, if the kip force wasn't in the center, it would spread more to this column. See how more of the force is on this column than on this column?
Yeah.
It was over here. See the force spread out. See how more of the force is on this side, on this column?
Yeah. Oh.
More of the force is on the right side than the left side, or the left side than the right side.
Right.
Right in the middle, forces are equal. Pretty good in the hood. So this is going to be a reaction force of 10 kips because it's 20 kips right there in the middle. 10 kips. We also have a reaction force right here. And that's going to be 75 kips. Because 5 KLF times 30 feet is 150. Divide that by 2, 75 kips. And you have the base right there at G. So we're gonna find the internal the internal axial force in here. So this is what Kleb was saying earlier. So let me just take this off real quick. So imagine so there's weight right here, correct? There's weight right here.
Mm-hmm.
There's a weight right here. And then there's some weight right here. Oh, okay. Some weight right here, and then there's some weight right here. So we're just going to look at this column real quick. So we're just going to take this column out of the picture. So now we're just left with half of this load, half of this load. I'm just going to take out half. And then I can't really take out half of a single block, but you get the gist. I'll just move this over then.
Yeah.
So you have this load and this load.
Huh? Okay, I'm coming.
So where should you cut it? You should cut it where both of the loads are on the same side. So you have to cut it like down here. So let's just cut it right there. So you see how it's all on the same side?
Mm-hmm.
You cut it up here, then you're either left with this load or this load, but not both of them at the same time. So we're just going to cut it right at the bottom. So like, see, this is the floor. We're just going to cut it right at the floor, and that's our cutting point. Very
Gotcha.
simple.
And that's where you get that point G.
Yeah. That's
the
going to be our
bottom.
point G. So you're just going to point this going up. I'm actually going to point these going down because point these vectors going down. That's what he did apparently.
Yeah, I was about to say, I see that in his drawing as well.
Yeah, I didn't take hand notes. I took
The
notes.
digital notes, yeah.
Digital notes because I'm dumb. So they're pointing down because the weight is spread across. So it's like going down, but it's like spread across. Like, yeah. Hopefully that made sense. Probably not, maybe. I don't know.
It did.
Okay.
Better than my notes, which is no notes.
All right, so we're just gonna finally take care of this. Gonna take all the summation of all the forces
In the Y, right?
in the Y direction. So I'm going up.
So
It's
everything
in the Y direction.
Everything's in the Y.
So remember, this is an internal force. This is a axial force. So it's going to be P. Yeah, P sub G. So you have PG. That's going up, so it's positive, minus 75 kips. This is going down minus 10 kips.
Yep.
So just PG is equal to 85 kips.
Yes, sir. That is the maximum axial force. Point G.
Yep.
In that column.
So if you don't, so like it's just pushing down with the force of 85 kips. If it's not graded to that level, then it's just gonna collapse. It's just gonna break. So like another thing he kind of went over is like, you know how he was talking and like buildings are like thicker at the base. So you can also kind of see that here. So you have two forces right here. If you cut it right here, it's going to be a lot. But if you cut it right here, there's just one force. So this column doesn't need to be as thick because there's less kips acting upon it axially. Does that make sense? I hope that did.
Yeah, and that's where he drew his little.
Yeah.
I know. I get it.
All right, that's all the
So you
all
can
the
think
things
of it
I
as
want to
like a
go over.
tree.
What's
Because a
that?
tree, you can think of it as like a tree, like a pine tree, where it's real thin
Yeah.
at the base, and as it grows, it gets thinner at the top.
Yeah. All right. So did I miss anything? Is everything all good in the hood?
Oh, I got one thing.
What's up?
Imran, your food's ready.
My food's ready. My food's ready. I should have muted my mic, man. God damn it.
Right, I'm gonna stop the recording unless y'all have anything to say.
Oh no, you didn't wait. Didn't you guys hear my mom earlier when she was coming to pick up my cat?
I heard that. I heard that.
Yeah. So see, so
I heard that too.
it balances out, Imran.
But I feel bad. I should have muted my mic.
We're all good. We're all good.
Yeah, I muted my mic right away. I was like, oh, wait a minute now.
I just responded. I was like, I'm coming. I'm coming. This knowledge is. I eat knowledge instead. I eat knowledge.
All right. I'm gonna stop recording right now.